The first things that we're going to cover in this lesson are the remainder theorem and the factor theorem. And to be perfectly transparent with you, the only reason I'm covering this is because you have homework questions, but these theorems are a little outdated since we do have calculators. But the remainder theorem states, suppose that f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. So example 1 says find the remainder of f of x when it's divided by x minus 3 and x plus 2. So here, if I'm dividing by x minus 3, if all I want is the remainder and not the quotient, all we need to do is plug in this 0. So if you do x minus 3 equals 0, this means we have a 0 at 3. Or I guess really the question is, do we have a 0 at 3? So I now need to plug in this 3 to both of these x's here. So we have f of 3 equals 3 cubed minus 4 times 3 squared minus 5. So we'll put this in our calculator. And we have 3 cubed minus 4 times 3 squared minus 5, and we get negative 14 as the remainder. Now I have a note right here. This is the same problem as Module 2, Lesson 8, when we did example 3B on page 105. So here is that problem here. When I used synthetic division, I ended up getting a remainder of negative 14 by just plugging in that value. So if it just wants you to find the remainder, you could go through synthetic division or long division to get your remainder. But if that's all that they need, the easiest thing is just to plug in that value and it will give you the remainder. So finding the remainder, if I divide this polynomial by x plus 2, that means x equals negative 2. So now I'm going to substitute in negative 2 for both of these x's. And we definitely need to make sure this is in parentheses. And let's substitute in. Or I guess we already substituted in. Let's evaluate. And we get a remainder of negative 29. Now, to piggyback off of that, we have an important and useful consequence of the remainder theorem, and that is the factor theorem. So the factor theorem states that if f of c equals 0, then x minus c is a factor, or vice versa. If x minus c is a factor, then when you do f of c, it should equal 0. We kind of dealt with this a little bit in lesson 7 when we were finding factors and x-intercepts of polynomials. So use the factor theorem to determine whether the function f of x has a factor of x minus 1 and x plus 2. So we really treat this the same way. This is, we're wanting to know, do we have an x-intercept at x equals 1? So plug it in. We're going to find f of 1. And what I am wanting to know is when I plug it in, do I get 0? If I get 0, then this is a factor or an x-intercept. If I don't get 0, then it is not. So we have 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. Plugging it in for all 3 of those x's. And we do get 0. So because I get 0 right here, this means that x minus 1 is a factor. Okay, so let's see if x minus 2 is also a factor when we have x plus 2. When we have x plus 2, that means x equals -2. So now I need to find f of -2. So I'm plugging in a -2 for all of those x's. And here we have a double negative minus from the function, and then what I am substituting in is the negative. Okay, so I'm changing all of those ones to -2's, and we get -27. So 1, that tells me the remainder, but to answer the question, this means that x plus 2 is not a factor.